Hello everyone, good afternoon. Uh, Let us wait just a minute so that anyone else joins in the last moment. So let us begin. I am Subhadeep Day. I am faculty at IUCAA and I'll be taking 3 lectures under this summer school program. Uh, the thing that I will cover is the atomic clocks, the technologies that are used to build the best atomic clocks in the world, and what are their applications. And this entire thing is I have divided into 3 lectures. Today is the first one, and then tomorrow and day after tomorrow at the same time. This is like about 1 hour lecture. I would take a break somewhere in the middle, and I will try to take few questions at that time, and the remaining questions as much as possible at the end of the talk. So when I take a break, you please raise your hand if you have any questions, and then I will go one by one. So let me begin. In this first lecture, I will talk about the basic of the atomic clocks, basics, and I will give a brief introduction, not only the atomic clock, but to some extent to some associated things to general physics and then atomic clocks. Then explain the basic principles of the atomic clocks. And today I will also discuss about the microwave clocks. The microwave clocks are of two different kind. One uses atoms at room temperature or slightly higher than the room temperature. We call it hot atomic clock. And the other one is ultra cold atoms. Those uses like laser cooled and trapped atoms, which are nearly at 0 degree Kelvin. So these are the 4 things I will try to cover up today. To start with, let me start with very basics, because there are several students who are joining these things, so it might help them to, let's say, understand, or maybe to start with, to get to this field. So being a human being, we have an inquisitive mind, and due to that, we try to explain everything what we see around. And this around means basically starting from the of the universe. Let's Big Bang. This is the picture what you have probably seen several times during the summer school by several other people. So this is like evolution of the universe starting from the Big Bang. We are in the Earth, and we try to explain all things starting from how the atoms are formed, what are the ingredients of the atoms, how the molecules are formed, and then more and more and more how the planets are formed and everything, and how they are held together and etc. Okay, so being physicists, we try to explain the physical phenomena, and for that we use different kind of models to explain them. Like for example, we this is a very like let's say very simple picture, and this shows like classical physics, then quantum physics, then there are many other things like, let's say, string theory and so on so on. There are relativity, general theory of relativity, and these different models we use to explain different physical phenomena. At present, we are actually going to the second quantum revolution, and quantum physics is a very good model which explains many of the physical phenomena, but not all. It also has open questions. It was kind of, let's say, hypothesized during the early 1800, but the real beginning of the quantum mechanics was by Max Planck in 1900, and the word quantum mechanics was given by Max Born in 1924. So it's about, let's say, 120 years, the journey of quantum physics. And during these 120 years, we have learned several things in the quantum mechanics or quantum physics, And now we are in an era where we actually use quantum mechanics or quantum phenomena to build different kind of sensors or detectors or different kind of instruments. But still, as I said, there are many open questions in the quantum mechanics. For example, the gravity cannot be explained by quantum mechanics. Yes, we have to do much more to do that. So this is, for example, one example where I can tell you what are the still remaining like openness of the quantum mechanics. We know that there are four fundamental forces in the nature, and these are strong force, weak force, electromagnetic force, and gravitational force. Without going into detail of these forces, I am sure all of you know about these forces. Like, for example, strong force, this keeps the nucleus or the quarks together within the neutron, proton, and electrons and other particles. The range of this force is on the order of 10 to the power minus 5, and the strength of these all four forces are considered relative to the strong force. So the strength of the strong force is considered 1. Similarly, there are weak force, which is responsible for the nuclear decay, and relative to the strong force, their range is 10 to the power, their strength is 10 to the power minus 6. The electromagnetic interactions, that is probably we experience all of us, that is like two charged particles, they either repel or attract depending on their charges, and their strength is 1 over 137. These are called like fine structure constants basically. Yeah. And the fourth one is gravitational force. That's why I mean, we know gravitational force. That's why an apple falls downwards, and that's why the entire universe is formed due to this gravitational force. So far, so good. So the quantum mechanics can actually explain strong force, electromagnetic force, and weak force, but it cannot explain the gravitational force here. One of the main reason is we don't know. I mean, for any kind of forces, for this quantum to explain it by quantum theory, we need a particle, a boson, a carrier particle, boson, which carries this force. And for gravitational force, the graviton is yet to be detected. We believe there is a graviton particle called graviton, but it's not yet detected directly. This is one of the reasons why quantum mechanics cannot yet explain the gravitational force, but for the other three forces, it explains very well. Still, there are open questions. Even though it explains all three forces, in these all three interactions also, there are open questions. And this model of explaining this strong interaction, electromagnetic interaction, and weak interaction by quantum theory, it's called standard model of particle physics. And the open question of the standard models are like, why there are only 6 kind of quarks, why there are not, let's say, some other quarks than what we know, or why there is a let's say dark matter or dark energy, how they originate, and so on, many things, the violation of symmetries, violation of constancy of the fundamental constants, and many more. So we need to do several experiments and together with the theory to explain this kind of phenomena, even with our known knowledge of the standard models. And the typical experiments, they are in two different energy sectors in terms of, let's say, energy. There are high energy experiments and there are experiments which are at very low energy. For example, here you see this picture, it's from this reference, which shows some high energy experiments to describe different physical phenomena. For example, let's say the neutron star, how they merge together, or the dense quark, and so on. These are all high energy, and the highest level of energy that mankind have reached by in a controlled experiments, let's say, that's at LHC, and that's around 13 tera electron volt. The corresponding temperature of that energy is 150 times 10 to the power 15 Kelvin. On the other hand, there are very low energy experiments, and low energy means typically very close to 0 degree Kelvin, very close to the absolute zero. And these are called ultra cold atomic experiments. So the atoms or ions, they are cooled to nearly 0 degree Kelvin, and you can do very precision experiments using them. As you see, here are some picture of this MOT, magneto-optically trapped atoms. I will come back to MOT later and during my talk. Then the BEC, Bose-Einstein condensation, they are at around 100 nanokelvin temperatures. And then trapped ion experiments, they are typically at 10 microkelvin temperature. So very, very low compared to orders and orders of magnitude low compared to the high energy experiments. And both of the experiments have their advantages and disadvantages. The high energy experiments, but I mean, even though they are in two different energies, basically by doing these experiments at two different high energy and low energy sectors, we try to explain the basic things of our nature, like why this symmetry violates, or why that symmetry violates, or why there is a how these interactions are held, like keeping the particle together and etc. The only difference is we take different paths by these different experimental approaches and try to explain the basically the similar or same fundamental questions. And if all these different kind of experiments gives a similar or same answer, then we say, okay, this our model, for example, the standard model is actually a good model. If you give an answer in one way but the other approach doesn't give you an answer, then we are not sure whether this model is correct or not. So that's why all these kind of experiments are very important to do. But it's very important that we do all this kind of all experiments, not only one approach. Just to give you an idea about what kind of energy here we are talking about, like this Big Bang, the energy during the time of Big Bang was 2.5 times 10 to the power 76 tera electron volt. So this is like way lower compared to let's say LHC can reach. During the Hiroshima Nagasaki, it was on the order of 10 to the power 20 tera electron volt, whereas the cosmic microwave background is only 2.73 Kelvin. Yeah, so basically in the low energy sector, the controlled low energy experiments, mankind have reached much lower temperature compared to the naturally available lowest temperature, which is CMB, cosmic microwave background. So in an experimental way, we have actually reached to nearly 0 degree Kelvin. Yeah, and the reason, the advantage of using this very low energy is basically you can do very precision experiments by that. Then there are different type of experiments. In some experiments, it's a big consortium, many people involved into this kind of experiments. For example, these astronomical detectors, gravitational wave detectors, telescopes, etc. Several countries are involved into it. Similarly, let's say Fermilab, G-2 experiment, high energy experiments, basically CERN, LHC, let's say this neutrino detector, super Kamiokande neutrino detector in Japan. So these experiments are some of the examples. There are several more than these few examples where different countries, several people, a big number of people with a large collaboration involved to do this kind of experiments. However, there are another set of experiments where it can be done tabletop in a single lab. Maybe few people can do these experiments, and these are typically atomic physics experiments, and ultra cold atom experiments are examples of that. For example, here I am showing parity non-conservation experiment, or measuring electric dipole moment, or again parity violation experiments in using trapped atoms, and of course atomic clocks. And in all four examples that I am showing you, they use ultra cold atoms or ions, which are at nearly 0 degree Kelvin temperature. And all of these are basically led by single group and a tabletop experiment, but they are very precision experiments. So you can measure things very accurately or precisely. So today I will be basically focusing on this atomic clock part, but not the other ones. As I started my talk with the quantum mechanics, how it evolved in last 120 years. Of course, it started with this, let's say, these fundamental rules like quantization of the energy, or uncertainty principle, or wave particle duality. Then in between, during the 90s, people realized the actual Bose-Einstein condensation or Fermi degeneracy in the experimental way. And then now we are in an era of using this quantum phenomena of particles and building actual instruments. And few of the examples, such examples are like quantum computer. Quantum computer use uh, quantum nature of the particle, like entanglement, superposition, so on, so on. Then atom interferometers. We know about Michelson interferometers for very, very long time. But now the most precision interferometers, even much, much precise compared to the photonic interferometers like Michelson interferometers, are atom interferometers, because atoms also have a wave nature. And using that, using ultra cold atoms and then like interfering their wave natures together, one can do atom interferometers and can measure actually G very, very accurately in space and etc. And people are building these atom interferometer based gravimeters basically. Then quantum communications and atomic clocks, which are actually basically very good sensors, very accurate sensors, which can sense several things. And I will talk about those things during my last lecture basically. So during that, in this last 120 years period, the clocks has also evolved. And the reason it had to evolve, because clock have very like unavoidable applications to do several of the experiments, or let's say the very sophisticated technologies, and so on, so on. For example, communications and etc. I'll talk about more about the applications during my last lecture. So as you see here in this plot, this is like over last 700 years how the accuracy of the clock has evolved, and the y-axis is basically saying the running time of a clock over which it gives 1 second inaccuracy. So if I just focus on this last 120 years, which you see this yellow shaded region, and there you see like about 120 years back, a pendulum, free pendulum clock was accurate to 1 second over about an year time scale. So a pendulum clock typically is like gives 1 second inaccuracy if it runs for a 1 year time scale. From there, in 120 years today, we have reached to an accuracy where a atomic clock, the best atomic clock, is inaccurate to 1 second over 35 billion years. So just remember that age of our universe is 13.8 billion years. So it's 3 times more than that approximately. So a clock, supposedly there is a clock, atomic clock, which was running for last 35 billion years until now. Today it will give only 1 second inaccuracy. So certainly the question is, who cares about that kind of accuracy? And I would try to do my best to tell you that this kind of accuracy is actually needed for several applications, including technology as well as finding fundamental science, looking for fundamental science. Okay. So let me first tell you what is the basic of a clock. Irrespective of it is atomic clock or pendulum clock or quartz clock, whatever, the basic is actually same. Basic is you need a periodic oscillator which oscillates periodically over time, and you need a counter which can count these oscillations one by one without doing any mistakes. So if you, now the question is, how do you make this oscillator? For the oscillator, you can choose either pendulum or atom or quartz or sundial or something else, which some natural phenomena or artificial phenomena which has a very good repeatability, and some other additional instrument to count that repeatable phenomena. That is the basic of any clock. As you see in this video also, that's what it is showing. And then by finally you have a display to display these things. So once you have a very periodic oscillator, very repeatable, some oscillating, some phenomena which is happening in a very repeatable manner, and a very reliable counter which is counting without doing any mistakes, then you can build a very accurate and stable clock. So for this kind of instrument, particularly for clock, these two words are very important: accuracy and stability. So something is very accurate and accurate over very long period of time, that is the stability. And mankind has tried different oscillators for last 700 years or so, starting from, let's say, sundial, then different like water clock, then candle clock. About 30 years back, it was the rotation of the earth, that was Greenwich Mean Time. We know about that. Many people, many of you probably have are familiar with GMT. Uh, that was based on one complete rotation of earth, that is very periodic, but that also have some disadvantages. And at present, atomic clock. So what was the problem with, let's say, pendulum clock? So here I'm trying to explain that problem using this small clippings from this movie Kyamat Se Kyamat Tak. You see there are two pendulums, and if you look carefully, you see these pendulums are not oscillating in a synchronous manner. You see, you look at it carefully. So these pendulums are not oscillating synchronously, and that is the actual problem. The problem is you can try to build pendulums as good as possible, but since these are human made, these pendulums cannot be identical to each other. And that is actually the problem with all kind of oscillators except atom. The advantage with atom is they are identical in nature. You can take an hydrogen atom here or anywhere, they have same compositions, identical compositions, so they have exactly same feature. That is the main advantage of using atomic clock. So most commonly used oscillators at present are quartz and atoms. Quartz, I mean, all of us we use wristwatch and etc. And they are based on this quartz clock. Quartz is basically a crystal. It has a piezoelectric property. So you apply some voltage, the length of the quartz crystal changes, and if you apply an let's say oscillating voltage, then you get a length change of this crystal very periodically, and it's quite accurate for our daily purpose. Let's say I want to start this meeting and I was delaying 1 second. This is, for example, you don't need an atomic clock to do this kind of works. But if you want to do other things, for example, let's say GPS communication, navigation, we all use navigation systems today. We all use Google Maps and so on. For those things, quartz oscillator is not good enough. You need to have the atomic clock, where the accuracy is several orders of magnitude better compared to, let's say, the quartz clock. So the concept of atomic clock, was first given by Professor Rabi in 1945. In 1944, he won the Nobel Prize for NMR technologies. And then after 1 year, he came up with the idea that atoms can be used as an oscillator. And remember, that was the time of Second World War. So at that time, the radio frequency communication was used by all these, let's say, developed countries for this during this war, for communications and several other things. So there they felt the importance that this radio frequency to use this radio frequency communication, they have to have a very good clock. A quartz clock or rotation of earth is not good enough. And they were searching for an alternative option, what can give a very good frequency reference, or in another way, a very good clock. Frequency is just inverse of time. And then Rabi came out with the idea that atoms can actually serve the purpose, and that is what you see this paper cutting from New York Times in 21st January 1945. There it was first not published, but it was came to the public, this idea. The reason this atomic clock is very good, as I already told you, they are identical in nature. Their frequency of the oscillations, like periodicity of the oscillations, is on the order of 10 to the power 10 to 10 to the power 15 hertz. So if you are in 10 to the power 10 hertz, it is microwave region, and if it is in 10 to the power 15 hertz, this is in optical region. Yeah, so as the frequency of the oscillations is very high, you can actually build a very good clock, and you can understand it in the following way. Let's say you have some oscillator which is oscillating once per second, and then you have a counter which is counting that oscillations, but none of the counters are perfect. There is always some error. Nothing in the world can be perfect. Everything has some error. So assume that counter is missing one count. So that means it's missing 1 second, because the pendulum itself or the oscillator itself has 1 second oscillation time period. Now, if you have the oscillation frequency very fast, like let's say 10 to the power 10 times it is oscillating per second, in that case, if you miss 1 second, sorry, one oscillation, if the counter miss only one oscillations, that means it's missing 1 over 10 to the power 10 seconds. So a very small fraction of 1 second you are missing by missing one count. And if you go to optical domain, then it is 1 over 10 to the power 15. So a much smaller fraction of a second you are actually missing by miscounting just a one count. And that's actually the reason why a atomic clock, even atomic clock at different frequencies, or let's say higher frequencies, gives a better accurate clock. And that's the reason why the rotation of Earth is not a good enough. Of course, you won't miss the entire one rotation of the Earth. That is not possible. But even if you miss a fraction of that, that's also like a fraction of 1 day. That's why some oscillator which is oscillating very fast gives you a better result or more accurate clocks. And then the other thing, advantage of the atoms are, it's a very stable oscillator. Like if you can take these atoms anywhere else in the world or even outside of the world, it gives the same, it has the same nature. No aging, like quartz. If you take the crystal, it's also, it has some aging effect, like over the time due to the environmental reactions and etc. Its property will change. So piezoelectric property will slowly change. But for atoms, it doesn't. The atom which was during, let's say, immediately after the Big Bang, and today the hydrogen atom have the same property. It has not changed. It's most unperturbed system. Like, of course, you can say that it interacts with the electric field and magnetic field, but we can very accurately estimate that or measure that thing, exactly how much is the change. So it's nearly unperturbed system compared to any other oscillators. You can trap and cool them, so that means you can keep them in a very well controlled environment, and then you can do a precision experiment. So if you keep these atoms in a very well controlled environment, that will allow you to do very accurate or precision experiments. So these are the advantage why atomic clock is the best if you want to make any accurate clocks and etc. So here is a table which shows different type of atomic clock. So the first row is quartz clock, which is not an atomic clock, which is a crystal clock. But just to give the comparison, I kept the quartz also there on the top. And then there are different atomic clocks like hydrogen maser, rubidium clock, and cesium clock. These three are in the microwave domain, or let's say radio frequency domain, on the order of 1 gigahertz to 9.2 gigahertz or 10 gigahertz, this frequency range. And you see their accuracies are between 10 to the power minus, let's say 11 or 12 to 10 to the power minus 14. And these are all, these three clocks are room temperature, or let's say slightly above room temperature clocks. As soon as you use cesium, the same cesium atoms, but you cool them to nearly 0 degree Kelvin temperature by laser cooling and trapping techniques, and I will explain these things more in detail. Then you can increase the accuracy to 10 to the power minus 16. So at least 2 orders of magnitude better compared to the hot atom clocks. And the present best clocks are in the optical domain, which uses neutral atoms and ions, but in the optical frequency range, and also cooled to nearly 0 degree Kelvin temperature. They are even 2 to 3 orders of magnitude better compared to the microwave clocks, because the frequency is higher. And during these 3 lectures, I will cover these microwave and optical clocks, the details of those things. Today, I will try to cover the microwave clocks. So when you want to, I will focus on using atoms as an oscillator. And for atoms, for any atomic clock, irrespective of whether it is a microwave clock or it is a, let's say, optical clock, the basic thing is it requires atom-photon interactions. You have to excite the atom to an excited state by a photon, and that photon can come from RF, radio frequency, or can come from laser if it is an optical domain. So let's say the atom is in to start with it's in ground state, that is G, and then if you apply the external field either by RF or by laser, depending on the excitation frequency, it will go to the excited state. The excited state has some lifetime, that is tau. So after that time, it will again decay back to its ground state. And this scattering rate is called gamma p, which is the maximum scattering rate gamma. This capital gamma is actually inverse of lifetime of the excited state, times S0 is called saturation parameter, that is depends on the strength of the external field, and delta is detuning. Detuning is how much this external field is detuned from the actual resonance frequency W0. Let's say your external frequency is slightly lower or higher than W0, then you will have different probability of transferring the atoms to the excited state, which is called Rabi oscillation basically. So that's basically the basic principle of using atoms as an oscillator. So you have to have an atom photon interaction, and this photon can be in RF domain or in optical domain, depending on whether it is a microwave clock or an optical clock. So this is how the atomic clock works. As I said, you have to apply the external field and then it will be excited. Then after a certain time, that is lifetime of the excited cell, it will decay back, and you measure this fluorescence or whatever in the form it is signal. And then if you change the detuning of this external field, that is if you go away or beyond this frequency nu0, you will get some sort of Lorentzian spectrum depending on excitation probability. You measure that. In that way, if you measure this Lorentzian spectrum, then you will get two parameters from the spectrum. One is the central frequency nu0, and one is full width half maxima, that is delta nu of the spectrum. So that if you can measure these two parameters, or basically measure the spectrum and then derive these two parameters, then you can feed it back to your external excitation laser or microwave, and you lock that frequency at the nu0, and you will be able to basically have a reference of nu0. Yeah, and then once you have the reference of nu0, you can derive the time. Let me show you how you do that. Let's take the example of cesium clock, which is actually the present definition of international standard of seconds in SI unit. So cesium is a very good candidate for microwave clocks, and the reason is it has only one naturally available stable isotope. Other isotopes are radioactive, maybe slightly radioactive, but still radioactive. It has a doubly splitted ground state, which is at 9.2 gigahertz, and that is a very narrow transitions in the microwave domain, and it has only one electron, one valence electron in the outer cell. So the electronic structure is also very simple. And as I explained in my previous slide, so this doubly splitted ground state of cesium atom, that is F is quantum number, is equals to 3 to F is equals to 4. This frequency difference is 9,192,631,770 precisely. So if you measure that frequency by this technique, let's say, as I explained just before, then you can basically say 1 second is nothing but the total time taken for this many number of oscillations. And that is the present international definition of 1 second. If you take a different atom, then this oscillation frequency will be different. For example, for rubidium, it is 6.8 times 10 to the power 9 oscillations approximately. So if you measure that many number of oscillations, that's not 1 second. So 1 second is internationally defined for 9,192,631,770 oscillations. That is the oscillation frequency basically between hyperfine splitted ground state of cesium atoms. So people have measured by different techniques this frequency, transition frequency of cesium with an accuracy of 10 millihertz, on the order of 10 millihertz. So 2 points after the decimal point, 2 digits after the decimal points. So for these microwave clocks, I already told that to you that there are two different times. One is at hot atomic clocks, or basically room temperature clocks, and other one is fountain clock, which uses ultra cold atoms, and I will explain both of them in my next few slides. So let's start with these hot atomic clouds. There, the instrument is following. You have an oven which consists of cesium atom, and cesium atom, it has two ground state, a hyperfine ground state, and this ground state, let's say, are defined by these two tiny magnets. So the nuclear spin is so you can consider the electron spin is coupled by the with the nuclear spin, and the electron spin is, there is only one valence electron, so the electron spin is only one half, so it can either align let's say topwards, upwards, or downwards with respect to the quantization axis. So that means the electron spin, if you consider it as a magnet, it is like either looking in one direction, like upward direction, or it is in the opposite direction, and that is actually defined by these magnets. So you see these magnets are just opposite to each other, and that is defining two states, just for the explanation purpose. So normally the cesium atoms inside the oven will be mixture of 50-50 mixture of these two tiny magnets, or 50-50 mixture of atoms in these two different hyperfine states. So if you heat this oven, then if there is a small opening here, let's say in the oven, the atoms will come out, and that we call atomic beam, and in that atomic beam there will be again 50-50 mixture of atoms in two different states. So the first thing what we have to do, we have to apply a magnetic field gradient, and that does the Stern-Gerlach effect. Basically, due to this magnetic field gradient, this one type of two different electron spin will move in two different directions. We know what the Stern-Gerlach experiment does. That way, we throw out one set of magnets, and then we only keep the magnets which are, or atoms in this case. When I say magnet, means these are like cesium atoms at F is equals to 3 state, and then we take these atoms at F is equal to 3 state, we put them through a microwave cavity. And if we apply, and if we don't apply any microwave in this cavity, then it will just pass through. And then there is a second stage of the Stern-Gerlach magnetic field, where we apply magnetic field gradient again. And if we don't do anything in the microwave cavity, this will again move, this remaining cesium atoms will again bend to another direction, but will not do anything else. Now, if we apply the microwave at the right frequency, let's say 9.192731660, 631,770 hertz, then these atoms will be excited. So these magnets will flip its direction, or the atoms will go from F is equals to 3 to F is equals to 4 due to this external microwave field. In that case, what will happen? This second deflector, or the Stern-Gerlach stage, that will deflect this magnet again to a different direction, and if we keep a detector here, these atoms will fall into the detector. So if we arrange the detector in such a way, so after deflection it will go towards the detector, then we will be able to see the signal in the detector. That way we can say that whether our microwave source is at what frequency. If we apply the correct frequency, we get the maximum signal in the detector. And that way we will be able to calibrate that microwave frequency exactly. We will be able to say that this microwave frequency is at 9.192631770 gigahertz. Yeah. And then once we measure that, that becomes reference of our timing systems due to considering the SI definition of second. That is, for example, a picture of the atomic beam clock, how internally it looks like. This is the oven. This is the actual picture actually. This is the oven, and this is the first Stern-Gerlach magnets. Then this is the microwave cavity. It's called Ramsey cavity also because it was first, this technique was first developed by Ramsey. And then this is the second stage of deflector, and this is the detector, how it looks like. And this is a real cesium beam clock at NRC in Canada, National Research Council in Canada in Ottawa. And this is about, I have seen that this is about, like, let's say 3 meter long, or maybe even more than that. This is housed in a Faraday cage. So you see all these walls are covered with copper plates. So no outside electromagnetic field, nothing can penetrate into it. So it can measure, it was able to measure the cesium frequency very, very accurately. But these are kind of the first generation cesium beam clocks. Now this entire technology is miniaturized into this small box like that. And this is commercially available by, it was first developed by HP, Hewlett Packard, now then Microsemi, and then again Microchip, another company. But it does the same thing, and it's actually more accurate than the NRC Canada clock, this clock. So you can see the transition of technology, this big, huge thing inside of Faraday cage and everything, it went to a small 19-inch box. It's the size of a computer CPU. Yeah, and it does the same thing. It has even better accuracy. It's just improvement of the technology, and etc., etc. So here I will take a pause and I will take few questions if you have any, and then I will go to the ultra cold fountain clocks. So please raise your hand if you have any questions. Yeah.
Hello, sir.
Yes.
Sir, you told that we put this whole assembly of clock inside this Faraday cage so as to reduce this electric fields, right? But what about those wires which are inside the systems, the currents that flow? So is there any significant effect due to those wires or those stuff?
No. See, though, the reason it is kept inside the Faraday cage and etc. to reduce the dynamic things. So let's say you have some residual electric field and etc. from, let's say, outside wirings etc. which changes time to time. That will influence the frequency measurement time to time, right? But if you put this inside of a Faraday cage, then you are not sensitive to this dynamic changes of electric fields or microwave. If something is constant, that is easy to take care of. If something is constant, which is not changing over time, then you can measure it very accurately, and then you can either subtract or add to your actual frequency measurement, and then you take it over. So as you correctly pointed out that there are some wires and etc., which is inside of the let's say heating the oven, you have to use some wires and etc., and you are passing some current through it, but that's not changing over time. That is a constant thing. Yeah, I hope I am able to answer your question. So the Faraday cage is only to suppress the environmental effects which are changing time to time. Do you understand? Yeah. Now, Neil.
So here we have talked about various oscillators and the frequency which we can measure. So how do we ensure that we have a precise measure of the oscillation?
How do you ensure
that the measurement of oscillation itself is precise, like the mechanism which we are using?
Yeah. So so that's a good question. So first of all, we have taken atoms as an oscillator, and we know what is the atomic frequency. And if we know that maximum transition excitation probability, that will tell me that the external laser or microwave have to be at that frequency. Then only you can get the maximum excitation. So atom is an ideal oscillator, ideal reference. That's what serves the purpose, but that's not all. Yeah. Now, if you do only one measurement, then you are not sure that whether your measurement can also have some error, like systematic error and etc. So you have to have multiple measurements from multiple through multiple different experiments and then combine them together. And that technique is actually called three-corner hat measurement techniques, or there are other techniques also. So only one atomic clock won't be able to tell you whether this is an actually absolute reference frequency you are measuring. You have to have multiple of them and you have to compare them. That's why in case of atomic clock, one important thing is intercomparison. You make a clock here, and let's say there is another clock in Japan, there is another clock in Germany, and then you intercompare them using satellite links or other links, fiber links nowadays. And then only you can say, okay, how this intercomparison of frequency will tell you how these measurements are accurate or not accurate. Do I answer your question?
Yes, sir.
Yeah, okay. So now, Sohum?
Sir, I'm sorry, I asked my question. I forgot to lower my hand.
Okay,
yeah,
no,
I
sorry.
got the answer.
Yeah. No, there is Sriya.
Good afternoon, sir.
Yeah.
Sir, my question is just a curiosity. Sir, I wanted to ask that before coming to cesium
Sorry,
atom
your voice is breaking. I cannot hear you properly.
Sir, one second. Sir, am I audible?
Yeah, now it's better.
Sir, my question is just a curiosity. I wanted to ask that before coming to cesium atom as a selection for the atomic clocks, did we experiment other atoms or maybe something else for selection of these?
Yes, sure. So it has started. So the history is actually much longer, which I did not cover. So it started with ammonia. The first atomic clock experiment was in ammonia molecule. So then people tried hydrogen, then people tried cesium, rubidium, and other things. So it's an evaluation process. So it evaluated through different systems, atomic and molecular systems, and finally people realized that cesium is one of the best candidate compared to all of them, and that's how it became the standard.
Oh, okay, sir.
Yeah. Okay, so there are no further questions at this moment. So let me go forward. So now I will be talking about the ultra cold cesium atom clocks. So as I explained you in the hot beam clocks, like the atoms passes through a microwave cavity, and if you have looked carefully, there are two interaction zones with the microwave in the cavity. So let me go back to this picture. So this is one interaction zone and this is the second interaction zone. This is not the interaction part. So microwave is applied here where atoms are interacting with them and atoms are again interacting with them. So the question is, why do they need to interact twice? That I will come. Why do they need to interact twice? But the point is, this is basically to get interference effect. That's why they need to interfere twice, and I will come back to that in a moment. But first, let me tell you that if this in between these two interactions there is a free fly regime, if you can increase this length of this free fly regime, that is the distance between cavity 1 and cavity 2, interaction zone 1 and interaction zone 2, then you will get much better interference fringes, much narrower interference fringes. So, but how long can you make this distance? You cannot make it like a kilometer. Yeah. So the other way of dealing these things is you cool the atoms to much lower temperature, so they take longer time to reach from interaction zone 1 to interaction zone 2. Let's say one atom is moving at 100 kilometer or few hundred kilometer per second speed. So it will take only a very small fraction of a second to reach from one cavity to the other cavity. But if you cool this velocity to 1 meter per second, instead of 100 kilometer per second, if you come down to 1 meter per second, so it will take much longer time to reach from cavity 1 to cavity 2. So your delta T will increase, and following the uncertainty principle, I'm not going through the detail of that. That is basically delta T is time and delta is energy. You know that, and then E you can convert into frequency. Then the fractional accuracy, that is delta F by F0. So delta F is line width and F0 is the central frequency. that tells you how accurate a clock is, this quantity delta F by F0. And then using this formula, putting it here, you can convert it into 1 over F0 times delta T. So if you increase this delta T, that is this flying time between two cavities, you can have a much better or accurate clock. So to increase this delta T, either you can increase this length, but you cannot do it very long. The other way is you can decrease velocity of these atoms so that you can increase this delta T. And decreasing velocity means cooling the atoms. So temperature of an atom is nothing but kinetic energy, half mv square. So as the temperature goes down, the velocity will be also going down, and as the velocity goes down or you cool them down, you can increase this delta T. And that is actually the advantage of using cold sample of atoms. One of the advantages. There are other advantages also of using cold sample of atoms instead of hot atoms. So for example, this delta F, which probably you can measure for an hot atomic beam clock with an accuracy of, let's say, 100 hertz, will come down to less than an hertz if you use very cold sample of atoms. And that cooling you do by a technique called laser cooling, using lasers. So let me quickly go through this laser cooling technique. But first, let us understand what is the temperature here. Here, as I already explained, actually, the temperature of the atom is nothing but kinetic energy of the atom. So in 1 degree of freedom, it's half kb. Kb is Boltzmann constant times temperature. So the laser cooling follows this process. So if you apply a photon, then photon will interact with the atom, and then there will be a momentum exchange, and the atom will also be excited to the excited state. We have learned about that. But then this atom will again come back from excited state to the ground state, and it will release one photon of the same energy. Now the innate momentum conservation in this case, in this picture, is 0, because you add one momentum of a photon and you release one photon. So you basically add some momentum and release the same momentum. So the net momentum change is 0. So there is nothing cooling and nothing is happening in this picture so far. But if you apply several millions of photons, let's say from a laser beam, in a laser beam, the photons are coming from the same directions. They are unidirectional. So the atom is getting the photons from the same direction, but while releasing, they are being released in all directions, all possible directions in 4 pi. So now what happens if you add all of the released photons momentum? They are vectors, so you have a direction. Vectorially, if you add them, it will on average to 0. There is no momentum change due to releasing of the photons. But there is only momentum change due to absorption of the photons from the same directions. So let's say if you absorb n photons, then the total momentum that the atom will get is n times h bar times k. K is the wave vector of the photon. So that momentum exchange is nothing but force. Change of momentum is force. So that way you can apply force to the atoms using laser beams. So many times people ask that how can you cool atoms using laser beams? I mean, you can heat it up, but people don't understand how to cool it. And this is the way of explaining these things, that how it can cool these things, because the photons are coming from a unidirectional thing, from the laser, but they're getting released in all possible directions. So that's why the net momentum change is towards the direction of the photon. So that way, if the atom have a velocity in some direction, and if you apply the laser from the other direction, so this momentum exchange or applying the force through this laser beam will slow down the atom, and slowing is nothing but reducing the temperature. This is some example, like for the barium atom. So the minimum temperature by this laser cooling technique you reach is called TD, Doppler temperature, Doppler limited temperature, and the corresponding velocity is Doppler velocity VD. So for example, by this laser cooling technique for barium, you can reach to a Doppler temperature which is around 0.44 millikelvin. So you can cool the barium atom by normal laser cooling techniques to almost 0.5 millikelvin. You can do further cooling, and you can go to even nanokelvin temperatures. and corresponding velocity is just 1.6 meter per second. Just to tell you some for comparison, in an atomic beam, the, let's say, most probable velocity of atoms, so you know the Maxwell's-Boltzmann distribution, most probable velocity, average velocity, and so on. The most probable velocity of atoms, let's say around 500 Kelvin temperature, is some 600 700 meter per second. So from there you can cool that, let's say for barium atom, to 1.6 meter per second, and that's how you can increase this delta T much longer. So this is already, I actually explained this laser cooling, how the laser cooling works, but the atoms will have velocity in all directions. It's not that it has only velocity in one direction. Velocity has a component in Vx, Vy, Vz. So that means you have to apply counter propagating laser beams in all three directions, X, Y, and Z directions. And the total force is written like that: delta is detuning of the laser, and omega d is the Doppler shift. If your atom is moving in this direction and the laser beam is coming from the opposite direction, the atom from the atomic reference frame, it will see a different frequency than the actual frequency of the laser, that is the Doppler shift. And this Doppler shift we know k dot v, so minus k dot v, sorry, and that is what WD is shown here. Due to this counter propagating laser beams, this Doppler shift will be different for two different laser beams, because let's say the atom is moving in this direction. For this laser, the k vector is along this direction, but for this laser, the k vector is along the same direction as v. So they will have just an opposite sign of each other. So from these two laser beams, the total force that atom will experience is written by that, where AC depends on the intensity of the laser, saturation parameter it's called. Delta is detuning, so how much the laser frequency is detuned compared to the actual resonance frequency, and omega d is the Doppler detuning. And we need this detuning to cancel this Doppler shift. So if this quantity is 0, then you can apply maximum force. So the denominator goes down, and then your total force increases, and then this is the total force as you see here. It depends on detuning and intensity of the laser. So basically this force is proportional, the laser force you can apply through this laser cooling techniques by this counter propagating laser beams is proportional to delta detuning. Now if you choose delta lower than the actual transition frequency, that is called red detuned light. Right? If you choose the detuning red detuned light, then you will get a negative sign here, and negative force means you are actually slowing them, pushing the force. I mean, it's instead of accelerating, you are actually cooling them down. So you need to have, basically the point is you need to have a red detuned light if you want to have a laser cooling. Otherwise, it will be heating. So the detuning decides whether it will be a cooling or a heating using these lasers. And here, this is actually measured spectrum, and this is in fact from my own PhD thesis. So this black spectrum, what you see is the Maxwell's-Boltzmann velocity distribution of barium atoms coming out of an oven. And once you do the laser cooling, you will produce more atoms at the lower velocity compared to this normal Maxwell's-Boltzmann distribution. So this green spectrum is actually for laser cooled atoms, where you modify the normal Maxwell's-Boltzmann distribution. Now further, it's so far is good, it's called cooling, but it's not confining yet. You have slowed down the atoms to a much lower velocity or lower temperature, but you have not confined them. For the confinement, you have to apply some magnetic field, and in the magnetic field, what happens? You will get Zeeman shifting. Yeah, you will get Zeeman splitting. So the magnetic field, what you have to apply here is in anti-Helmholtz configuration. That means the magnetic field profile is something like this blue curve, where at the center you have zero magnetic field, and on the both sides it's more or less linearly increasing its magnitude. And that you can this kind of magnetic field you can create by anti-Helmholtz coils. So two magnetic current carrying magnetic coils, electromagnets basically, but where the currents are oppositely floated. or circulated. So in this one, current is circulated along this direction. In this one, current is circulated along the opposite direction, and then you can create this kind of magnetic field. And then as a result of that, the Zeeman splitting will be just opposite on the both sides of the zero magnetic field, because the direction is changing. Even though the magnitudes are same on the both sides, changing in the same rate on the both sides, but magnetic field has a vector, so it has a direction. Direction is changing. So let's say a is equals to one state, which means MF is equals to -1, 0, and +1 state. They will be like this along both sides of the zero magnetic field. So this is MF is equals to minus state, this is MF is equals to 1 state, and MF is equals to 0 will be unchanged. They will not be experiencing any first order Zeeman shift. Now if you have a red detuned light, which is detuned from your F is equals to 0 state by some amount, let's say delta, red detuned, then on this side of the zero magnetic field, that is this green one, this laser will be on resonance with F is equals to +1 state. So if you have a laser beam from this direction, so atoms which are coming in this direction, they will be interacting when the atom is at that position of the magnetic field. It will interact with F is equals to MF is equals to +1 state. On the other side, if the atom is in this side, then it will be interacting with MF is equals to -1 state. It will be on resonance with MF is equals to -1 state. So basically what happens on both sides of the zero magnetic field, it will interact with two different states, because the different states are on resonance. So you need two different polarizability of the light. We know sigma plus and sigma minus helicity for circular polarized light. You need two different polarizability of the lights on for these counter propagating laser beams, so that the atoms can interact properly. And if you do little bit more math, as I said here, this is the same formula as before, but now we have added the magnetic field, so you will have the Zeeman splitting, which is also added here. And this is added with this total force due to laser field in this formula. And then if you do little bit more math, you can reduce it to this formula, where one part is proportional to velocity of the atoms, and the other part is proportional to where this atom is located, where let's say Z is equals to 0 is where the magnetic field is 0, and this is the Z is equals to negative side, and this side is Z is equals to positive side. So depends on position of the atom. So applying the magnetic field will give you a space dependent force, a spatially dependent force, where Z is equals to 0. If the atom is at the magnetic field 0 point, then it will not experience any force due to this part. But once the atom goes out of the center, out of the Z is equals to 0 position, then due to the value of magnetic field, some finite value of the magnetic field, it will experience some added force, and that is confinement. Confinement is nothing but, like, let's say I am staying in this room. As soon as I want to go out of this room, I will get a kick and I will stay inside this room. So that's what it is. That's a spatially dependent force, basically, what you get by adding this magnetic field and proper choice of the polarization of the light. What you get a Z dependent or space dependent force. So as soon as you want to go out of the trap center, or where the magnetic field is 0, if the atom try to go out of that position, it will get a restoring force and it will be kicked back to this zero magnetic field regime. And that thing is called trapping. And since you apply magnetic field and laser field together, it's called magneto-optical trapping, in simple form MOT. And this is the picture of confined barium atoms. Here you see this green dot kind of thing. These are actually, this green dot is actually real trapped barium atoms, which I was taking this picture during this is my PhD thesis actually. So this is about 50,000 barium atoms which are trapped by this magneto-optical trapping techniques. And this is the spectrum, measured spectrum, and you see this x-axis is detuning. This magneto-optical trapping works only with the red detuned light. So 0 is the undetuned. As you go below zero detuning, that means you have red detuning light, and it works, the most efficient trapping works at some red detuned light. And this green blob of things is actually about 50,000 barium atoms which are trapped within about 1 millimeter diameter spherical ball. The advantage of this cooling and trapping technique is you can create a very small sample which can be used for precision experiment. You can get very long interactions times. It's done in an ultra high vacuum environment, so there is no collision with residual gas, and so on, etc. And that gives a much precision, that allows much precision experiments, particularly the atomic clocks. So in case of fountain, this kind of magneto-optically trapped atoms are used instead of atoms which are at hot at room temperature. So this is what you see in this picture, like cesium atoms coming out of the oven. They are collected in some ensemble, like few 100,000 atoms, let's say. Then they are pushed upwards through this microwave cavity. So as they go upwards, they interact once through the microwave cavity. Then they again falls back due to the gravity, and they interact second time. So there are 2 times of interaction happening in this case also. Once the atoms are going upwards, and second once they are falling back through the same cavity. And then at the end you apply another laser light to detect the fluorescence, and that's called state detection. And between these 2 interactions, the atoms freely evolve. Due to their very small velocity, the time between these 2 interactions is much longer compared to what you can get in a hot atomic beam, and that gives a much better results. Okay, so this is like how it looks like. Let me skip these things. In fact, let me skip this one also, because I don't have okay, no, let me just quickly go through it. So what happens? The cesium atoms has a magnetic moment. The outermost valence electron has some magnetic moment, and the magnetic moment interacts with the external radio frequency or microwave that you apply in the cavity. So for the first interaction, first time when the cesium atoms are going upwards, these magnetic moments will try to persist due to this RF, and they will acquire some particular phase due to this RF. But then when it is freely moving, like it goes out of the cavity first time, it goes upwards and comes back. Due to this free time, these atoms will keep its phase information in itself, but the microwave has propagated. So the next time when it comes back and interacts with the microwave cavity again, the microwave will have a different phase than the atom acquired due to this first interaction, and due to this phase difference, they interfere. And as a result of that, what happened? This simple Maxwell's-Boltzmann distribution gets finer, how do I say that, like fringes, finer fringes. So this outer, like this thing is basically Maxwell's-Boltzmann distribution, but due to this interference, they get fine fringes in between them, and that allows delta nu, that is this fluid half maxima, much smaller compared to what you can get in a normal Maxwell's-Boltzmann distribution. So that way you can basically reduce, let's say, from 100 Hz to sub-Hz accuracy of measurement of the central frequency, and that's what you see in this thing, like this. This is basically Rabi flopping, and this fluid half maxima becomes less than an Hz. So we are able to measure this 9.192631770 Hz with an accuracy better than Hz by doing this technique. It's called Ramsey spectroscopic technique. Ramsey was discovering that technique, and by the way, Ramsey is also PhD student of Rabi, who first gave the idea of atomic clock. So Rabi, his student is Ramsey, and Ramsey further developed this techniques of the spectroscopic techniques, and also he got the Nobel Prize. So okay, so up to today there are only few fountain clocks in the world which are operational. For example, here are the list of fountain clocks, like ultra cold microwave cesium fountain clocks, and they have the best fountain clock have reached to an accuracy of a few times 10 to the power minus 16 at this moment. And this is a typical picture of a fountain clock from Swiss laboratory Metas. So here you see in this optics table, these are the lasers and optics arrangement to generate the right frequencies and etc. Then this is actually the fountain. So below there, it's an ultra high vacuum chamber where you trap the cesium atoms, magneto optically trap cesium atoms, then they are thrown upwards. Then the microwave cavity is somewhere here, then they goes upward through the microwave cavity and falls back, and on the back side you see lot of electronics which are necessary to operate and control entire thing. So this is kind of a very good state of the art technology. In India also, CSR National Physical Laboratory in New Delhi, they have a fountain clock which is accurate to fit something like 10 to the power minus 15 or so. So I will stop here today, and tomorrow I will start with optical clocks. But now it's open for questions. If you have any further questions, please raise your hand. Any more questions? Okay, I don't see any hands. Okay, so if there are no more questions, let us meet again tomorrow. Okay, now there is one question, Onsu Sharma. Hi, Onsu.
Good evening. Good evening, sir. Sir, in the earlier case, when you were talking about clock,
sorry, your voice is breaking. Your voice is breaking.
Affect in any way?
Onusha, your voice is breaking. Can you repeat? Hello.
Audible now?
Yeah. Now it's better.
Sir, earlier when you were talking about the cesium clock, does the Earth's magnetic field affect it in any way? Like on various locations, there is a slight change of the intensity of the Earth's magnetic field.
Yes,
so does it affect the clock?
Yes. So that is your question? Sorry. Hello.
Sir, I was asking, does that affect the clock?
Yeah, of course. This is a very good question. So Earth magnetic field is different in different places, and that actually affects the clock. So for that, what we have to do, and what we do actually, we sealed this entire chamber using new metal. New metal actually has a very high permeability, and it protects the magnetic field to come inside. So we use few layers of new metal shielding to protect them from Earth or any other ambient magnetic field. So the entire experiment is done within some new metal chamber, basically. Then I see there are few questions in the chat bar, and that is, within the short range of strong force and weak force, what is the speed of carriers of strong and weak force? Is it the speed of light? Why, I don't understand this question. Then the next one is, why Fermi condensate is not regarded as sixth state of matter just as BEC does? Why it's a sixth state of matter? It's not, it should not be Fermi. I mean, why it should be a sixth state of matter? I mean, I don't know what are the first 5 state of matter is. So I really do not understand what is this means. Then there is a question, what do you mean by F is equals to 3 or F is equals to 4? F is the quantum number. So like, you know, there are quantum number like n, and then if you add the nuclear quantum number and the magnetic quantum number of electrons, then you get F. So F is I plus J. J is total angular momentum of an electron, which is spin plus linear angular momentum, and then F is just a quantum number. Then how one can decide which part, that is 4 is equals to 3 or 4 is equals to 3, pass through the microwave cavity? See, that you select by the selector, this magnetic field. So you apply this Stern-Gerlach magnetic field in such a way that F is equals to 4 atoms bends in some direction and it doesn't come to your remaining of the experiments. Yeah, and then the rest of the experimental parts are kept on the path of F is equals to 3 atoms, which are after this first stage of Stern-Gerlach experiment. That's how you do it. Does Earth magnetic field affect? That I already told you. Why Fermi condensate is considered the state of matter, whereas B, C is, I actually do not understand what this question means. It's just two different kind of statistics. One is bosonic statistics, other one is fermionic statistics. There is no different state of matter. The state of matter is like liquid, gas and solid and plasma, sometimes people call, but there is no condensate is not a state of matter really. It's just two different statistics. One follows fermionic statistics, other follows bosonic statistics. In bosons, they can share the same state, but fermions, due to the Pauli exclusion principle, because they have spins, they can't be in the same state. So in the condensate, each fermionic atoms occupy one state. Then there is a last question in magneto-optical trapping. No, sorry. What happened in magneto-optical trapping? We are confining the atoms to a very small space. Then they should be very high. There will be very high uncertainty, so that the temperature of the atoms also so much uncertain. So how atom is said to be cooled? In magneto-optical trapping, we are confining the atoms to a very small space. Yeah, but I don't see why there is an uncertainty principle violation here. It's a very small space, but it's actually very dilute systems. 50,000 atoms over one, let's say 1 millimeter diameter. It's a very dilute systems. In fact, it's not a very dense systems. So I do not understand why uncertainty principle have to violate here. What uncertainty principle? A bit of out of the topic question: will an operational fountain clock work in the same manner at every point of the galaxy? Just a thought of the. Okay, so this is a very good question. Like whether, basically the question is whether an atomic clock will operate in the same manner everywhere in the galaxy. So that I will cover in the third lecture. Please remind me. There I will answer these things. It will actually not, probably. And that is the some experiments what people wants to do. But remind me, I will answer these things. Is laser cooling applied only between cavity 1 and cavity 2? No, laser cooled atoms are laser cooled initially, and then these laser cooled atoms are used for any further experiments. So actually there is no laser cooling between cavity 1 and cavity 2. At that time they are freely moving. But first you prepare the sample and then you use them for throwing them through the cavity. Okay, I do not see any more questions, and actually we have to close because there is a next speaker who is probably waiting. So in case if you have further questions, feel free to ask in the next talks also. Okay. Then closing this session. Okay.